Just as a reminder of what we've done before, if f prime is positive on an interval, then f is increasing on that interval. And if f prime is negative on an interval, then f is decreasing on that interval. So this gives us the first derivative test for local extrema. So, and you already did some of this on the weekend's assignment. Let C be a critical number of a function f, which is continuous on an interval containing C and differentiable on the interval, except possibly at C. Did we talk about critical numbers?
No.
Okay. So a critical number, might want to write this someplace. A critical number of a function is an x value where either the derivative of the function is 0 or the derivative of the function does not exist. So, and the reason why those are critical numbers is if you think about it, if we go back to our discussion of velocity, for example, if the velocity of an object is 0, well, it might change directions then. It doesn't have to change directions, but it has that possibility. It is a critical point. It's important. Something might happen there. Same is true where the derivative doesn't exist. If the derivative doesn't exist at a point, it's possible that the object will change directions. It's also possible that the function will not change directions. Just as a quick example, so people are like, well, I get how it can change directions where the derivative doesn't exist. But if this was our velocity graph, right? Velocity is going up, velocity now going down. You're like, okay, this is the object's motion. But what about, can it continue going the same direction? Yep. So if this is the path of the particle, here I have positive velocity and now more positive velocity. No, it's slower.
Oh, no. I embarrassed myself.
Chemistry is rotting your brain.
I'm dying.
All right. So the first derivative test for local extrema tells us that if f prime changes from negative to positive at x equals c, then f has a relative minimum at c f of c, which is what we were doing a few moments ago when we were looking at that graph of the derivative. The derivative changed from positive to negative. That means that the function changed from increasing to decreasing, and hence you have a local maximum. And vice versa, okay? So this is the first derivative test for local extrema. So let's take a look at this. The graph of the derivative, y equals f prime of x, of the function f of x is given here. Find the x-coordinate of each relative extrema of f of x. All right, so this is f prime, the derivative. Here at this point, the derivative changes from increasing to decreasing. That doesn't give you an extreme value on the function. It does give you an important point on the function, and we'll talk about that on Wednesday when we talk about concavity. But here at point B, notice the derivative changes from positive to negative. So what must be true of f at point B?
It's a maximum.
Yeah, f has a local maximum at x equals b. Okay, the derivative has a low point here at c. That doesn't cause a maximum or a minimum. Again, we'll talk about these high points and low points are actually important, but for another reason. Okay, now when we get to D, is the derivative 0 at that point? This is the graph of the derivative.
Yes.
Yes. So that is a critical point of f.
So if it wasn't the graph of the derivative, it was just the graph of x, could that be non-differentiable at that point? If it was more.
If this was the graph of f, this is differentiable. The derivative would just be 0. Right? But since f prime is negative, 0, and then negative, in that order from left to right, well, this is going to be neither a local maximum nor a local minimum for the graph of f. And do you see why it's really important that you talk about for the graph of f prime, on the graph of f, right? You can't say it.
All right.
Okay? What happens to the graph of f at point f?
It changes from the derivative, f prime of x, changes sign from negative to positive.
So what does that mean about f then?
It has a local minimum.
Correct. F has a local minimum at x equals f. Because f prime changes from negative to positive. Okay? All right, let's move on to page 2. So for this one, we want to find the interval or intervals on which f of x equals x cubed minus 3/2 x squared is increasing, and the intervals where it's decreasing. So the way that we'll do that is we will take the derivative, f prime of x, which is 3x squared minus 3x, and find any critical points. Critical points, again, are places where the derivative is either 0 or the derivative does not exist, either one. Is there any place where this does not exist? It's a polynomial. Polynomials exist everywhere. So that's not a problem. Always think about where it does not exist first. The tendency is to think about where it's equal to 0, which is important, but because there's usually work involved in that, then people forget to think about, well, is there a place where the derivative doesn't exist? And remember, primarily, with the functions that we deal with, there are 2 cases where the derivative doesn't exist. Zeros in the denominator of the derivative, and square roots that have a negative argument, okay, for the derivative. For this, that doesn't happen, so we'll set that equal to 0. We'll factor out a 3x. One of the most common mistakes, actually, after doing that is forgetting about the 3x and be so concentrated on this part that you forget, oh, yeah, 3x could be equal to 0 also. So we have 2 critical points, x is 0 and x is equal to 1. That is going to partition a number line into 3 segments, or 3 parts. I guess 2 of them are raised, but you get the idea. At 0 and at 1. And again, in this case, when we're looking at this, this is pretty clearly an upward-facing parabola, right? So that means that f prime is greater than 0 here, f prime less than 0 here, f prime greater than 0 here. And as we discussed last week, if it's not as obvious, pick a value in somewhere in this range, substitute it into the derivative, not into the original function, because we're interested in the sign of the derivative, and just figure out the sign. And that sign will not change in this portion of our number line. Okay? So, f is increasing on the interval from negative infinity, oops, made that a closed interval, and you can't close negative infinity, to 0, and from 1 to infinity. F is decreasing on the closed interval from 0 to 1.
Kind of sad that infinity and negative infinity get to be free and open. 0 and 1 are caged in.
Because they're zeros.
Well, and the other problem is that infinity is not really a number.
It's a concept.
Yeah.
An idea.
We're saying that it is unbounded.
Far beyond your puny human comprehend. Oh no.
Anytime someone says, puny human, I think about the Avengers where Loki is talking to the Hulk, and he's like, bam, 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 and he's like, puny god.
You can graph his motion, create a nice ups and downs.
All right, so find the x-coordinate of each local extrema of this function on the interval from 0 to 2 pi. So we'll take the derivative, f prime of x, and that'll be 1/2 plus sine of x. And again, we want to think about, is there any place where this is not defined?
No.
No, sine's defined everywhere. So we'll just find where that's equal to 0, which means we need to know where sine of x is equal to negative 1/2. So where is that?
1.
Gosh, no.
X equals
Sine inverse.
it's in the second quadrant, right?
No, sine is positive in the second quadrant. Remember the whole all students take calculus thing?
It could be the fourth quadrant.
Or the third? Y'all's unit circle is appalling.
Hey, it's good in the first quadrant.
All right, well, tell me where sine is equal to 1/2 in the first quadrant.
Pi over 4.
That's 45.
It's 45 degrees. That's where it's 1/2.
45 would be square root of 2.
Yep, 2 part, right?
It will be, well, I know it would be 30 degrees, pi over 6.
Pi over 6. Okay,
Negative
so
pi over 6.
now, but it has to be between 0 and 2 pi. Negative pi over 6 is not between 0 and 2 pi.
I don't know.
It doesn't exist.
This is not a good thing. 7 pi over 6, or x is equal to 11 pi over 6. Okay? Yeah, you gotta get better on your unit circle, guys. Seriously.
We should have a quiz over it on Wednesday.
I was about to say that. They're like, Jesus,
All right, so we're going to look at a number line for this, but we're only going to look between 0 and 2 pi. So I'm not going to put arrows on the ends of this. 11 pi over 6 is almost to 2 pi. And 7 pi over 6 is more than halfway. So if I substitute in some value between 0 and 7 pi over 6, say pi for example, That'd be a half plus sine of pi is 0. So f prime is positive here. And because we kind of know what this looks like, it's the sine graph moved up 1/2. So f prime is negative here, and f prime is positive here.
Oscillating.
Yes, that's what sine graphs do. So f has a what at x equals 7 pi over 6?
Local maximum. Extrema.
I'm going with minimum.
Well, f prime is positive here, which means f is
Maximum.
means f is
Increasing.
increasing, and then it changes to f is decreasing. So we must have a local maximum at x equals 7 pi over 6. What happens at 11 pi over 6?
The minimum.
Yes, f has a local minimum at x is equal to 11 pi over 6.
Oh, the Bill's probably spent so much time.
Pardon?
The unit circle.
Yeah, we spent a lot of time in the unit circle part trying to guess how the Bill's going to rank soon.
All right.
I need to study that quiz with me last year.
Instant.
Let's see. We don't have a ton of time left, do we?
We have Uno minute.
We have Uno minutes.
Uno minute.
We have 2 minutes.
Well, in 10 seconds.
Not enough minutes, Lance.
So here, notice this function does not exist at x is 0, right? That's excluded from the domain of the function. It'll also therefore be excluded from the domain of the derivative.
Oh, the quotient rule.
You can use the quotient rule, or you can rewrite this one to be x plus x to the negative 3. So then the derivative would be 1 minus 3x to the negative 2. We want to know when that is equal to 0. We already know that it doesn't exist at x is 0. So 1 equals 3 over x squared. So x squared equals 3. So x is plus or minus the square root of 3. So for my number line
Positive or negative square root of 3.
and 0, so pick a number. I'm going to use 1. Substitute it into the derivative. F prime here is negative. F prime here is positive. If I substitute a negative 1, I still get f prime negative.
Since we know that each of those is a sign change, if we found one, could we just know that every other one?
Yeah, got to be careful that there's not a sign change at 0.
Okay.
So
It's just a critical
here
loss.
f has a local maximum, and here f has a local minimum. And at 0, it has neither a local minimum nor a local maximum because the sign doesn't change and the function doesn't exist. You can't have a maximum or a minimum at a point where the function doesn't exist.
So we just label it for the heck of it?
Well, you could have a sign change there.